Q6205. If a wave were to form on a stationary front running east and west across the United States, that portion east of the wave would normally A. Remain stationary with that portion west of the wave becoming a cold front. B. Become a warm front, and that portion west of the wave would become a cold front. C. Become a cold front, and that portion west of the wave would become a warm front. The correct answer is B. When a wave forms on a stationary front running east and west across the United States, it typically leads to the transformation of the portions east and west of the wave into different types of fronts. In this scenario, a stationary front refers to a boundary between two contrasting air masses that is not moving significantly. When a wave develops on a stationary front, it introduces a disturbance in the otherwise stable atmospheric pattern. The wave is characterized by a region of convergence and rising motion, which causes the front to undulate or oscillate. The interaction between the wave and the stationary front can initiate changes in the air masses on either side of the wave. East of the wave, the portion east of the wave tends to transform into a warm front. As the wave develops, the warm air mass begins to advance and override the cooler air mass associated with the stationary front. This forward movement of the warm air mass creates a gradual slope or rise along the frontal boundary, transitioning it into a warm front. Warm fronts are typically associated with the arrival of warmer air, often characterized by gentle and steady precipitation. West of the wave, the portion west of the wave tends to transform into a cold front. In contrast to the advancing warm air east of the wave causes the cold air mass to advance and displace the warmer air mass to the east. This movement of the cold air creates a steeper slope or descent along the frontal boundary, transforming it into a cold front. Cold fronts are often associated with more significant weather changes, such as the potential for thunderstorms, heavy rainfall, and rapid shifts in temperature. In summary, when a wave forms on a stationary front running east and west across the United States, the portion east of the wave typically becomes a warm front, while the portion west of the wave transforms into a cold front. This wave-induced transformation leads to distinct weather patterns and changes in air masses on either side of the wave. 6206. Which statement is true regarding a cold front occlusion? A. The air ahead of the warm front is warmer than the air behind the overtaking cold front. B. The air ahead of the warm front has the same temperature as the air behind the overtaking cold front. C. The air between the warm front and cold front is colder than either the air ahead of the warm front or the air behind the overtaking cold front. The correct answer is A. In the context of a cold front occlusion, the air ahead of the warm front is indeed warmer than the air behind the overtaking cold front. A cold front occlusion occurs when a faster-moving cold front catches up and overtakes a slower-moving warm front. This merging of the two fronts creates a complex frontal system known as an occluded front. To understand the temperature distribution along a cold front occlusion, it's important to consider the air masses involved. A warm front is associated with a warm air mass, while a cold front is associated with a cold air mass. As the faster-moving cold front catches up to the slower-moving warm front, it begins to lift the warm air above it. This lifting process creates a situation where the warmer air ahead of the warm front is lifted off the surface and pushed aloft. The lifted warm air mass becomes sandwiched between the advancing cold front and the slower-moving warm front. In this configuration, the lifted warm air is no longer in contact with the surface, and its temperature begins to cool. Consequently, the air between the two fronts becomes colder than the air ahead of the warm front or the air behind the overtaking cold front. The result is that the air ahead of the warm front, which is being lifted and pushed aloft, remains relatively warmer compared to the air behind the overtaking cold front. This temperature difference is a distinguishing characteristic of a cold front occlusion. In summary, in a cold front occlusion, the air ahead of the warm front is indeed warmer than the air behind the overtaking cold front. The lifting and displacement of the warm air mass between the two fronts cause a cooling effect, resulting in a temperature contrast along the occluded front. 6207. Consider the following statements about mountain waves. 1. Mountain waves always develop in a series on the upwind, windward side of mountain ridges. 2. In a mountain wave, the air dips sharply downward immediately to the lee side of a ridge, before rising and falling in a wave motion for a considerable distance downstream. 3. If the air is humid and the wave is of large amplitude, lenticular, lens-shaped, clouds mark the wave's crest. 4. In a typical wave, the greatest amplitude is seldom more than 1,000 feet above the ridge crest elevation. From the statements above, select those which are true. A. 2 and 3. B. 1, 2, and 3. C. 1, 3, and 4. The correct answer is A. From the statements provided, the true statements about mountain waves are 2 and 3. Statement 1 is incorrect, as mountain waves do not always develop in a series on the upwind, windward side of mountain ridges. The formation of mountain waves depends on various atmospheric conditions and the interaction of wind with the terrain. Statement 2 is true. In a mountain wave, the air does dip sharply downward immediately to the lee side of a ridge before rising and falling in a wave motion for a considerable distance downstream. This is a characteristic feature of mountain waves. Statement 3 is true. If the air is humid and the mountain wave has a large amplitude, lenticular, lens-shaped, clouds can form at the crest of the wave. These clouds are often observed downwind of mountain ranges and are a visual indicator of the presence of a mountain wave. Statement 4 is not true. In a typical mountain wave, the greatest amplitude can exceed 1,000 feet above the ridge crest elevation. Mountain waves can reach much higher altitudes, and their amplitude depends on various factors such as wind speed, stability of the atmosphere, and the shape and height of the mountain range. In summary, the true statements about mountain waves from the given options are 2 and 3. Mountain waves involve a downward dip on the lee side of a ridge followed by a wave motion downstream. And if conditions are right, lenticular clouds can form at the crest of the wave. 6208. When flying low over hilly terrain, ridges, or mountain ranges, the greatest potential danger from turbulent air currents will usually be encountered on the A. Leeward side when flying with the wind. B. Leeward side when flying into the wind. C. Windward side when flying into the wind. The correct answer is B. When flying at low altitudes over hilly terrain, ridges, or mountain ranges, it is important to be aware of the potential danger posed by turbulent air currents. In such areas, the greatest risk of encountering turbulent air is typically on the leeward side when flying into the wind. To understand why the leeward side when flying into the wind is more likely to be turbulent, it's important to consider the airflow patterns around terrain features. When wind encounters a hill, ridge, or mountain range, it is forced to rise on the windward side. As the air ascends, it creates an area of relatively smoother airflow on the windward side of the terrain feature. However, once the air reaches the crest of the hill or ridge, it descends on the leeward side. This descent leads to the creation of turbulent air currents. As the airflow encounters various factors such as changes in wind speed, eddies, and turbulence caused by the terrain itself. This turbulent airflow can be unpredictable, gusty, and pose a hazard to aircraft. When an aircraft is flying into the wind and approaches the leeward side of a hill or ridge, it enters the region where the descending air creates turbulent conditions. The interaction between the aircraft and these turbulent air currents can result in sudden changes in altitude, airspeed, and control responsiveness, which can be dangerous if not anticipated and managed properly. On the other hand, when flying on the windward side, the aircraft is generally facing the oncoming wind, which can create some turbulence due to the airflow encountering the terrain features. However, the turbulent air currents on the windward side are typically less intense compared to those on the leeward side. In summary, when flying at low altitudes over hilly terrain, ridges, or mountain ranges, the greatest potential danger from turbulent air currents is usually encountered on the leeward side when flying into the wind. Pilots should exercise caution, anticipate turbulence, and be prepared to adjust their flight path and altitude to mitigate the risks associated with turbulent airflow in such conditions. 6209. Low-level wind shear, which results in a sudden change of wind direction, may occur A. After a warm front has passed. B. When surface winds are light and variable. C. When there is a low-level temperature inversion with strong winds above the inversion. The correct answer is C. Low-level wind shear refers to a sudden change in wind direction or speed that occurs over a relatively small vertical distance near the Earth's surface. It can present a significant hazard to aircraft, particularly during takeoff and landing, as it can cause abrupt changes in airspeed and control responsiveness. One situation where low-level wind shear may occur is when there is a low-level temperature inversion with strong winds above the inversion. To understand this, let's break it down. A temperature inversion refers to a layer in the atmosphere where the temperature increases with height, rather than the usual decrease. Inversions can occur for various reasons, such as radiational cooling of the surface at night or the presence of warm air aloft. When a temperature inversion exists near the surface, it can create a stable layer of air that acts as a barrier to vertical mixing. This means that air in the lower atmosphere, including the boundary layer close to the surface, may have different characteristics compared to the air above the inversion. In the presence of a temperature inversion, it is possible for strong winds to be present above the inversion layer while surface winds remain relatively light and variable. The temperature inversion acts as a boundary, preventing the mixing of air and causing a significant change in wind characteristics between the two layers. As an aircraft encounters this low-level wind shear, it may experience a sudden change in wind direction and/or wind speed as it transitions through the inversion layer. This abrupt change in wind conditions can affect the aircraft's performance and handling, leading to potential challenges for pilots. It's important for pilots to be aware of the potential for low-level wind shear when there is a low-level temperature inversion with strong winds above the inversion. They can utilize various sources of weather information, including terminal aerodrome forecasts, TFs, meteorological reports, METRs, and wind shear detection systems, to assess the current conditions and take appropriate measures to mitigate the risks associated with wind shear. In summary, low-level wind shear resulting in a sudden change of wind direction can occur when there is a low-level temperature inversion with strong winds above the inversion. Pilots must be vigilant and prepared to respond to these challenging conditions to ensure the safety of their flights.